you've seen them. Um, Okay. Maybe you've seen it. Sprinklers, they can be like this, just like single sprinklers that they sprinkle around, or a very common system are these center pivots, in which the field is round because there's a well in the center of the field here, and there's an arm that looks like this that has sprinklers, and they used to be the water used to sprinkle from here, but the newer and more modern center pivots, the water is sprinkled closer to the plants, and then you have less evaporation, and then it just goes around all around, just with one arm, and that makes your field to be round. So the advantage is that you can irrigate with these systems very large areas, and it can be automated, and you can also use machinery because in this case, and also for example with drip irrigation, you have all of your equipment, it's in the field. But here, if the arm is just here, let's say the arm is resting here, then the entire rest of the field you can go in with machinery, and the irrigation system, it's not in your way. And also it has a very good potential for even distribution. If you can see, these fields are very green and homogeneous, because you can, if this system is well managed, you can have a very uniform distribution of your water. And some of the disadvantages is that it's low efficiency because you have a lot of water that's being evaporated, so you waste a lot of water, and also you're not irrigating just the root zone, but you're irrigating the entire field. So here, for example, you're also irrigating the middle of the row, which has no crop. That water is just going to be evaporated, and it's not creating any yield. There's a lot of evaporation. Also, if there's a lot of wind, then the distribution is less efficient because then you have no control where the water is going. Also, it's a high energy. You need electricity here to pump the water from the well, and you need electricity to move this pivot around. And even here you need water under pressure, and water under pressure means energy. Also, you can have a lot of weeds because you're just irrigating the entire field, and even diseases because you have to irrigate a lot of water in the environment for your plant to get the amount of water. So if you are in a humid environment, then some diseases can develop. But there are a lot of improvements via technological applications. You can have irrigation zones, like you don't have to irrigate the entire area if you have different crops, or if you know that your soil here it's a little bit different than here. These systems are computerized, so a computer can tell the system here irrigate a lot, and then here irrigate a little bit less. You can also use lower sprinklers like here, and even lower. Some systems, they just have, it's almost like drippers that they just go on the soil, and therefore prevent the evaporation and the wind effect. So from here we move on to drip irrigation. So these are all pictures from the R&D where I work. These are pictures that I took. So a drip irrigation system, it's a system in which the water is applied by little holes in a pipe directly to the plant. So here you see there's no crop yet, but you can see that the system is very stable. So it's very heterogeneous, right? This soil here, it's completely dry. This soil here, so this is the growing bed. We're going to grow here like these tomatoes. So it's getting ready for tomatoes. So here the soil is very dry, and you can see each circle, it's one dripper. In this case, it's every 30 centimeters. We have a dripper, and there's many in the market. There's many pipes with different spacings, and also with different discharge rate. In this case, each dripper gives you 1 liter per hour. So in the way the system works, you apply water with pressure, and the drippers, which are embedded in the pipe, they are pressure compensated, which means that in a large range of pressure of the water inside the pipe, you still get the same discharge rate, so the same amount of water per hour at that point. So that means that here we have 1 liter per hour, but also here at the end of the field, we also have 1 liter per hour. And then you can know exactly how much water each plant is getting. So sometimes this is the same width of bed. This is moringa, the same width of bed, but there's 4 lines of plants. So there's 4 lines of drippers. And the advantages are the very high water use efficiency because you're not irrigating all your field, you're just irrigating your plant. We call it crop per drop, so that every drop of water is just it's for the crop, for the yield. There's also increased yields. So growers, I was working before I was here, I was working in California, and growers that were growing processing tomatoes, they went from 40 tons per hectare to 70 tons per hectare. So from 40 to 70 when they switch from flood irrigation to drip irrigation. So they had what the water was available. They just switched the irrigation system, and their yields went high. There's very good weed control because here, if there's no water, then there's no weeds. And also, you can really improve your fertilizer efficiency because you can fertilize through the irrigation water, and also you're not wasting fertilizer in the middle of the row. You're just giving it specifically to your plants. But some disadvantages also include that they have very high initial costs, that they can clog. So there's each dripper here, it's one entity, and if the water it's dirty, if it has sand, if it has a lot of salt, organic matter, then the drippers they can clog. There's need for maintenance, like suddenly if an animal is chewing on your pipe here, the pipe bursts and the plants over here are not getting any water, so it has a maintenance. You can also have because of the high efficiency, if your water is saline, then you can have salt buildup, and then it needs to be that salt needs to be washed, and also that you need a pressurized system, that you need the electricity, you need to have water under pressure. But some improvements can be efficient scheduling. You can really make your irrigation scheduling very, very precise, because this system can allow you to irrigate half an hour 3 times per day, to know exactly how many times per day you need to irrigate. And also you can include leaching fractions, which means that if you have salinity problems, you can leach the salts by irrigating a little bit in excess. Which I will also talk about that later. So here, this is an experiment I did with onions. So that's why I was happy. I was hearing that some colleagues here are growing onions. And indeed, it's the same field I was showing first. So it's the same field. These are tomato plants in 2 rows, and these are onions so there's 6 rows of onions with 3 drip lines. So it's the same irrigation system. It's just the drippers, they were laid out differently. And also another disadvantage is that if now we finish the crop and we want the machinery to go in to rebuild these beds, then you need to take out the dripper. You can't work the soil with the drippers in it. You need to move them aside and then reinstall them, and that's what we do here. And then some solution is to do subsurface drip irrigation. So it's still considered a drip irrigation. Here, as you can see, you can't see the pipes, right, where the pipes are. So there's one pipe in the middle of this growing bed. These are also tomatoes. This is a picture I took in California of processing tomatoes. There's one pipe here at a depth of 30 centimeters below the ground. Then that allows that The irrigation system, it stays there for 7 years, and the machinery can go in and harvest the tomatoes and work the soil. But then the fertilizer is being applied also through the irrigation, and there can be many irrigation events. You can see there's no weeds here in between the rows, and it's very efficient. Also, it can prevent damage of the pipes by animals that can go and chew on your pipes. But if you have under animals that live underground, like gophers, for example, then you will have leaks underground, and then you need to go and identify those leaks. And also the maintenance can be a little bit hard because you need to dig to get to your system. Now, if we continue a little bit more about I said one of the disadvantages is that for drip systems you need pressurized water. Then some companies have been working on systems that they work on a low pressure. So if you have some water here, this maybe it's 1 meter or a meter and a half height, then you have that pressure of water, and they are building systems. So I know of two Israeli companies, maybe there are more companies around the world. I know about Netafim and Endrip, that this pressure, it's enough pressure for the drip irrigation system to work. And this is, you see here, this is corn, and I have another picture. So this is the water reservoir. So you need to fill this water reservoir, and then the pressure of the water standing on this tank, it's enough to drive the water through the irrigation pipes in the field. So that's also another option, and it's a good option for smaller fields. Then other methods that I haven't seen with my own eyes, but I know them from the literature, are, for example, clay pot or pipe irrigation. So if you have an unglazed clay pot and you fill it with water, then the water will seep slowly into the soil, and then the plant will have available water only when it needs it. The soil will take the water through the clay pot as it gets dry. So this is for like one pot per plant, but also it can be installed in pipes in the system. And there's also they're called sub irrigation systems, in which water is being fed into the field from below. Also, if you have a tile drain system, in which you have your entire field is drained with tiles below the surface, then you can also add water. So in some places where the groundwater is very shallow, you can increase the groundwater level so that the plants can have access to that water and then drain the field. Personally, I don't have any experience with that kind of systems. So now we move on to the next question, which is when to irrigate. So now let's say you have an irrigation system, then okay, do we irrigate every day? Do we irrigate once a week? Do we irrigate twice a week? It really depends. So it depends on the crop demand. So if the plant is very small, then it needs very little water. So this is an initial stage of corn. And as the crop develops, then generally annual crops, they have a steep increase in their water needs. This also happens with tomatoes and also with onions. Then suddenly the plant grows and it needs a lot of water from day to day. And then there's a little bit of a plateau until the plants, they are almost ready to harvest, and they don't need so much water. They're really ripening their yields, and there's less need for water. And then on top of that, you have the atmospheric demand. So maybe your plants are very small, but you started during a very, very hot time. Like if you start a crop sometimes here, for example, we start growing bell peppers in September. So we are on the northern hemisphere, so the winter is in December. So September is still very hot. So the plants are very small, but it's very warm. So then there's the need for water is higher. And then as the plants grow bigger, it's cooler, so they do need the plant itself needs a lot of water, but the atmosphere is demanding less water. Then also soil properties. So if you have a soil like I'm going, see if I can go back. I don't know how to go back. But I was in the pictures I was showing before. If a soil is very sandy, like the soil we have here that I was showing with the drippers, then it doesn't hold a lot of water, and maybe you will have to irrigate every day or sometimes twice a day if it's also hot and you have a sandy soil. But I was showing the picture in California that soil is very clay, it can hold a lot of water. Then even if it's very hot, then you can irrigate every other day, or you can spend some days in between the irrigation because the soil is holding that water, and that water is available for the plants. And also it depends on your irrigation system. So if you have a drip system, it's very easy to turn the irrigation on and off, but if you have a flat system, then it takes time to set it up for the water to go, and then you're not going to irrigate every other day. You will need a longer period. So again, I go back to these graphs of some of this place. I don't know how to say it, Blantyre, maybe in Malawi. That there's some times of the year in which is warmer and sometimes of the years in which it's cooler, and that's the atmospheric demand. Also, if you have precipitation, some precipitation, or you're growing during a time that there's no precipitation at all. And then regarding the soil properties. So I was talking about a soil that's sandier and a soil that has a lot of clay, and that will depend. So that's the texture of the soil. It will define the water holding capacity. So the larger the water holding capacity of your soil, the longer the time that you can spend in between irrigation events. And we have a relationship between the pressure of the water being held in the soil. So here you see this is water being held in the soil. So that water is being held under negative pressure between the particles of soil and the water content. So at the same pressure head, so this is a graph, it's called the retention curve, and it's the relationship between the pressure in the soil and the water content. So what it sees is that this is the sandy soil, is that as the pressure drops, so it's less negative. These numbers are actually negative, they're just in a log scale. As the pressure drops, then the soil gets immediately here. As the pressure drops, the soil gets immediately emptied with water. And in a clay soil, as the pressure drops, the water content is still high. So this is here the water content. So knowing your soil, it's very important for planning your irrigation, and also knowing if you have differences in the soil in your field. If you have a field that's large, then maybe one area of the field can hold the water, the soil can hold the water better than in other areas of the field. And even without irrigating, you might notice it, because if it rained and then one area is getting really dry and then the other area it's still doing fine, the plants are still green and the soil it's still wet, then you know that maybe it's your soil. Um, so then we have soil moisture sensing technologies. So we have sensors that they can measure either the pressure of the water being held in the soil or directly the water content, but they have a relationship. So you can measure both, and then you can monitor what you can't see. You can monitor underground. So many times farmers, you can go around and look at the soil and just check, right? Is it getting dry? Is it still wet? If it's too wet, then you don't need to irrigate. If it's dry, then you decide to irrigate. But depending on the crop, maybe you want to see, okay, what's happening underground. And if you have a large field, you can have sensors in places that are maybe farther away from you. So there's a lot of technologies. This specific, they're called tensiometers. So this is, you see, this is a pressure gauge. So this pressure gauge is giving you the pressure at this point in the soil, and that pressure, depending on your soil properties, on your soil texture, it's a measure. It can be easily related via the retention curve, that curve I showed you in the graph in the slide before, to the water content. And then sometimes you want to look at the water content at different depths. So this is just a diagram of that tomato field in which we had sensors at different depths. And then you can see, okay, this is getting drier, okay, but when this gets really dry, then it means it's time to irrigate. And some companies are now selling, this is a probe that has one sensor here, two, three sensors. Then you can see you start irrigating, and then when you see that water arrive here, then it's time to close the irrigation, because you don't want, if you have a drip irrigation system in which you have a lot of control, then you don't want the water to pass the area of the roots, because if you have water below your root zone, that's water that's being lost. So this is what that kind of data can look like. It's just one example. This 9 a.m. it's each day. And you see this is one day, so there's the morning, and then there's not so much is going on. Then the plants are using water, so this is the water content. The water content goes down, and then in the evening maybe there was some precipitation, nothing is happening, and then on this day it's getting really, really dry, very, very, very dry. It's so dry that the grower decides to irrigate, and then the water content goes back up again. So this is the brown is the tension, and the blue and green are the water content, but it's the same trend. So many times growers decide to monitor their soil conditions using these sensors, and nowadays companies are selling the sensors already with some like a cloud services in which it tells you what's the forecast, and it gives you a lot of information of your field that you can get from above. And then we get into the question, which is golden, of how much to irrigate, which me as a professional soil and water, many times, they ask you, how much should I irrigate my garden? I have a lemon tree. How much should I irrigate? When talking about crops, there's these definitions, which is crop water requirements. So I have references at the end of this presentation, which I will send it to you so that you can go into those references. So the crop water requirement. So this means how much water the crop needs, which can also be defined as actual evapotranspiration, or crop evapotranspiration. So it's the evaporation and the transpiration. So how much water is being lost from the soil via evaporation, and how much water is being lost directly from the plant as transpiration. But that's the entire how much water is being used. And that's calculated as a crop factor. So this is a unitless factor multiplied by the potential evapotranspiration. So this is how much water is being demanded by the atmosphere via the fact that is it cool? Is it hot? There's a lot of humidity in the air, or is it very dry? Is there wind? No wind? How many hours of sunlight? It includes all of that, and I will show how it includes all of that, minus the precipitation. So this is how much water is needed, but then if you have precipitation, then you need to add less water to your crop. And this crop factor really depends on your specific crop and on the time of the crop. So if it's the beginning of the season, the end, do I have the graph? The end. So here I was showing this graph for corn. So at the beginning of the season, this is the crop coefficient. It's around 0.3 and then it goes up as linearly with the crop development until it gets to 1. So then the potential reference evapotranspiration is that's how much water you need to add to your plant, and then it decreases. So now you're asking, okay, now I'm not growing corn. I don't know when or where this corn graph was developed. So I found some, I will show that I have some data for the crops in Malawi, and these graphs and these crop coefficients are developed by the extension services or researchers or the FAO and different NGOs for specific crops in specific places. Now this gives you the crop water requirements in millimeters, the same way as you measure the precipitation in millimeters. But if you want to know actually how much water you need to have for your field, so how many liters or how many cubic meters, then you need to multiply by your area. So if you have the crop water requirements in units of length, you multiply, so it can be millimeters, centimeters, meters, but it's units of length. You multiply that by your area, let's say 1 hectare or 100 meters square, and that gives you units of volume, and that's volume of water. So we say that if you had 1 liter of precipitation in 1 meter square, that's 1 millimeter of precipitation. The same we do with the irrigation. We calculate it in a length unit in millimeters, and then to bring it to actual liters of water, you have to multiply by the area, the area of your field. So you can say, I'm irrigating 10 millimeters per day, and it doesn't, because I'm irrigating my onions 10 millimeters per day, then it doesn't matter the size of your field. Then if your neighbor also has onions, they can also irrigate 10 millimeters, but each one will irrigate the specific amount depending on the size of their field. So how, before we go to the actual crop factors, how do we get these crop factors? How do we get to those numbers? So the classic way is to use lysimeters, which is something that I use a lot here in my research, that are containers that hydrologically isolate the volume of soil from its surrounding and have a drainage exit. So you can estimate the actual amount of water that the plants are using because you know how much you apply. So you know the irrigation, this is the I. You know the drainage, so you're collecting how much water this plant is not using because it has a drainage collection system. Here you see it from above, but it has hidden a collection system. And these containers are generally also located on a scale. And then you know, is the soil getting drier or the soil getting wetter? And if you had no precipitation on that day, you do irrigation minus drainage minus the change in the storage of the water in the soil, you get the crop evapotranspiration. And that's the crop water use, how much water this crop actually use. And then you can have that this is the crop water use, so the crop evapotranspiration equals this crop factor multiplied by the potential evapotranspiration of that day. And if you have the crop water use and the atmospheric demand, then you can estimate this crop factor. And this is how they are being developed. And then this crop factor can be used for that crop in that area for any year and for any time. So for these crop factors, sometimes the areas are divided into irrigation zones depending on the weather and on the crops that can be grown. So here you see Malawi is in area 16. The numbers are small, but it's area 16. And then the crops are being divided by different groups. And what I saw here is that there's an option to grow, for example, cereals, which can be maize, millet, rice, or wheat, either on a summer crop, right, from October to March, or on a winter crop between April and September. Because the weather is not so cold. If you have an irrigation system, then there's 2 seasons in which you can grow, and these crop factors, they change with the season as the crops grow, but also they can change if you're growing on a different time. And here they are divided by months, so that it will be, I think it's easier. Like you say, okay, in January, I'm irrigating 1.18 of the potential evapotranspiration. On February, a little bit less, but also they can be defined by the crop stage and not only by the month. So here I also see there's also for onions, are probably many of the crops that you grow, but more they can also be found. Now, how do we get this reference evapotranspiration? This potential evapotranspiration. So there's a very worldwide and very common method which is called the Penman-Monteith. That's a Penman and Monteith. They develop this equation in which that by measuring different environmental variables, they estimated a reference evapotranspiration. So sometimes it's like a grass, or sometimes it's just bare soil. It's just some evapotranspiration that is reflected only by the environment, and it doesn't take into account the crop. But then to take into account the crop, you have this crop factor, this Kc. So to measure this potential evapotranspiration, there's a lot of technology included. So it's a weather station. It has this has a rain gauge, and this is here this wind speed and wind direction and the temperature and also solar radiation and so on. And it has this very complicated equation. So this is the ATO potential evapotranspiration, the reference evapotranspiration. It has the net radiation, so that's the sun. Then the soil heat flux, so that's the soil part, the wind, the temperature, the vapor pressure deficit that's related to the relative humidity of the air. This is a constant, and also another constant. But then you say, okay, but how do I know what's the reference evapotranspiration today for my field? There are models that are giving data. So there's measurements being happening worldwide, and then there are models that can interpolate that data to any place in the world. This website, it's called Open Meteo, and I haven't checked how accurate it is in Malawi, but generally in my field and between my colleagues, it's agreed that it's quite good. And it can also give you the evapotranspiration, the potential evapotranspiration for the last few days, but also it can give you a forecast. So if you want to plan your irrigation for the next few days, you can use this forecast. So I show here how to use it. This is the website. So you click here, try the API here, and then you put here your coordinates. So you can go, for example, to Google Maps and put a pin of your field and get your coordinates. And here also you set the time zone to Malawi, and there's also automatic. You can tell it do it automatically according to the latitude and longitude. Then here, okay, no, okay, here you say which time. So do I only want a 7-day forecast, or do I also want past days? Or you can select a time interval. Then automatically here, this hourly temperature will be clicked. You don't need hourly weather variables to schedule irrigation. But if you scroll down, there's daily weather variables, and you want to look at the reference evapotranspiration. So this is this Penman-Monteith reference evapotranspiration that you need in your equation. And also you can look at the rain. Maybe if it's the rainy season, you want to see, okay, is it going to rain? If there's rainfall in the forecast, then maybe I don't need to waste my precious irrigation water. I will wait a few days. Then you click here, reload chart, like you scroll down, it's all the same. You see, it's all the same screen, and then you get this nice data. So this is I put actually a point these are the coordinates. It's somewhere in center of Malawi, and I have data between May 26th until June 15th. So I made a forecast. Maybe if you were there, there was a little bit of precipitation on May 27th. So the dark blue is precipitation sum. So it was less than a millimeter. So maybe it was not so important. And you can see how on average you're around 3 up to 4 millimeters per day of potential evapotranspiration. And then you click here, download Excel file, and you get this Excel file. So you get this is the potential evapotranspiration, and this is the precipitation in millimeters, and you go back here to your equation. So you have your potential evapotranspiration from that graph, you have the crop factor, and you have the precipitation. Then you multiply that by your area, and you know how much water. Oh, I see that I don't have. I'm missing the table with the crop factors that I put for. I'm going back. I'm sorry. Here. Okay, we have it. I thought I didn't have it. So you have your crop factor from that table, and then you can estimate. Now, you might say, okay, I don't have an irrigation system. How is this related to me? But if you're planning on setting up an irrigation system, you can use this just theoretically to estimate how much water then you would need. If you had an irrigation system and you wanted to grow, for example, a crop in the winter, in the during the dry season, then how much water that onion crop will take you if you want to grow it between May and September. And this framework can help you get an estimate. And now the last question, which is water quality, and I'm happy I put some onions. So this is not my research. I put the reference down here. But if you have a fresh water, then you're one of the lucky people in the world. You get a very nice onion crop. But as the salinity of the irrigation water increases, we know that there's a reduction in yield. So sometimes it's a reduction in the vegetative growth. So maybe the plant, the green part of the onion, or the green part of the corn is smaller, but then also the yield is smaller. So we have also, this is for tomatoes. So as the irrigation salinity increases, the yield decreases, and then depending on the salinity of your water, you will decide which crops you will grow or which varieties you will grow, so that you can still have some advantage of having this crop, and it's not going to be completely non-profitable because the water was too silent and the yield is too small. And there's a lot of research that's been done, and there's models that and coefficients that will define which crop or how sensitive that crop is to salinity. And here is some examples of some crops, and this is the graph of the relative yield. So as the salinity increases, the yield decreases, and the shape of this graph will depend on the crop. And here are the coefficients for different crops. So this is really only in a place where salinity is an issue, then you need to look into this. But if you know that your water is it's fresh and it doesn't have any salinity problems, then there's one less problem that you need to look into. So then, and if you have saline water, then to that crop water requirements, you add a leaching fraction. So you irrigate a little bit in excess consciously to leach the salts, so that the salinity in your root zone won't get too high, and then your plants will die. And that's what we do with all the crops that we grow here in the Arava. So again, yes, I said I have a picture from the Arava at the beginning and at the end. So these date palms, we are now sometimes in the summer, at the peak of the summer, they're being irrigated 1 cubic meter of water per day. That's 1,000 liters of water per day per tree. And that includes around the 30% of the water that's just being used to leach the salts away because the only water that we have for irrigation it's very saline. So I put here some resources. Um, of the mainly from the FAO, which are very practical and very good, and also the Open Meteo from all the graphs and all the tables that I put in this presentation. So thank you so much for listening and for inviting me. And I'm if there's time for questions, I will be open and will be happy to take any.
Oh, thank you so much, Era, for the comprehensive presentation. It was quite enlightening. Colleagues, let me open the floor. If you've got a question, please just raise your hand. And comments, question, just for 5 minutes. Any question?
Maybe if someone wants to comment, if you have an irrigation system, which type of if any of it is similar to anything I show, I'm curious.
Yeah. Anyone who is using surface irrigation, drip irrigation. I've got some drip irrigation per farm, and also we do use some surface irrigation as well. That was very helpful. Anyone who is using some irrigation systems? I was planning to set up an irrigation system. Anyone?
Okay.
Comments? Okay. All right.
So you're welcome to share my email with
Yeah.
the with
Yep.
with the participants, and
Yep.
if there are any questions later, then you're welcome
So what
to
we've done, what we have done is we've formed a WhatsApp group. So maybe what I can do is once we have maybe people have got some questions, etc. I can invite you on the WhatsApp and then you can respond
yeah,
directly
so that
to those
everyone can
questions.
see the answers.
Absolutely, it'd be good for us to learn from one another, and then yeah, sure, sure. All right. Yes, Wesley, do you have a question?
She's saying she's using small sprinklers and surface irrigation.
Oh,
Okay,
okay. Thank you.
thank you.
Yeah, I just wanted to respond. I've already indicated on the chat box.
Okay. All right. Wonderful. Wonderful. So just to complement your presentation, tomorrow I'll bring on a WhatsApp group an irrigation engineer who is also running an irrigation company so that we kind of contextualize whatever you've presented. Here I'll check on you if you have time. Just you can be when the guys presenting on the WhatsApp group, you can be there just to add one or two
Okay.
things. Yeah, sure, sure.
Yeah, as I
That's
said,
what I'll do.
the irrigation subject it's very large, and
It's
I
very
don't deal
large.
with any of the hydraulics, and I don't set up the irrigation system. It's
Yeah,
I work mainly with lazy meters, and I look at the scheduling and how much water, when to irrigate, how once the system is there, how to optimize it. And I think many times, people can set up, like a company can come and set you up with this system, and sometimes they have a agronomist and irrigation specialist that will guide you. It's important to take this information on, or have your own studies and your own decisions on how much to irrigate and when to irrigate to optimize. You just want to optimize your resources once you have the system.
yeah, yeah, sure, sure. So I think the guy we are bringing tomorrow, he sells irrigation equipment. I think almost everything you have said here, so it'll be helpful. Yes, Dr. Patrick Chisepo. Yes, Doc.
Um, no, thank you so much for the very detailed presentation. I've learned quite a lot. Of course, I am still learning and also thinking of some sort of irrigation. I wasn't sure what sort of irrigation I'm I can go for, but I think this learning is helping me to think about. Currently, I'm in a place where it's very hot cloud. Wow, so I think this knowledge is helping me now to think and um, issues of the amount of water that would be needed to irrigate. Yes.
Well,
Wow, thank you so much, Dr.
thank you so
Giuseppe.
much. Mhm.
Yeah, Hugo Odimba, any thoughts on our work with small scale farmers that we are doing in Madisi? Hugo Odimba?
Um, Hey, Funio, thank you so much. And also thank you, Hoffman, for a wonderful presentation. Just as Chief Funio is asking, so we as an organization, we've been thinking of some small scale type of irrigation for smallholder farmers, something affordable for them. And I know you show something like a gravity type of irrigation, but we would love to explore other options for our small order farmers. So in case there's more system or cheaper system for our farmers, I think for us, we would love to explore that and see how we can pilot it probably with our farmers. I just don't want to learn, but I also want to see if I can put those into practice. So if there will be any recommendation of small scale type of irrigation for our smallholder farmers that are working with, I think that would be appreciative. And we probably can speak in depth in regard to that. So other than that, I'm very grateful for today's presentation. Thank you.
Yeah,
Thank you. Yes, I think it's a matter. I'm not aware of what's being right now offered in the in your area to the growers because
Mhm.
you do need to have a supplier, and I know that the low pressure the gravity drip systems have been very successful in many places, but I don't know regarding how cost effective they are. It's I think each location needs to do that those calculations. It also depends where the water is going to be coming from and the energy costs. It's there's a lot to take into account, but I agree with you and with Chifuniro that the irrigating can really bring to the agriculture to another level in your area. That the potential it's very high, but maybe doing an assessment an economical assessment before installing any system, it's important to choose the most efficient system.
yeah, wonderful.
Thank you.
Wonderful. Yes, Charles, you raised the hand. I think that's the last question for the sake of time. Charles?
Oh, all right. Uh, Thank you so much for the training. It has been eye-opening to us more especially when we have to be in that.
We
I just
cannot,
wanted
you're
to,
not clear, Charles. Can you be closer to the mic, please?
all right. Thank you so much for giving me this opportunity. And it is an eye-opening seminar. So I have one question that I wanted to ask. For us beginners, what is the best irrigation system that we can use more especially in Mangochi?
I think let me take that one. Tomorrow I'm bringing Luano Menibabu on a WhatsApp group. He'll be able to answer that question. I think he's in Malawi. He's selling irrigation equipment. He installs different irrigation systems. So you'll be able to tackle that question. Since AR lives in Israel, he has never been to Malawi. So I think we'll tackle that question tomorrow. I think tomorrow we'll talk what can work in Malawi. I will bring this presentation to the context. Thank you so much.
Thanks.
Yeah, sure. Thank you so much, colleagues, for your participation today. I believe it was very enlightening, as I'm saying. Tomorrow, if not on Thursday, likely on Thursday, tomorrow, if not Thursday, based on Luano's availability, we're bringing Luano Meliwau. He's running a very successful irrigation company here in Malawi. He's an irrigation engineer. He's a lecturer at Luana, and he will take us through a session. Yeah, he's also coming there for business. So please, let's buy his product. Otherwise, thank you so much, everyone. Wishing you a lovely day. Yeah. Thank you so much.
Thank you.
Todalaba. Shalom.
Thank you very much. Shalom. Thank you. Good luck.
Hello.
You.